Welcome to another GCBASIC demonstration. This is part 14 for the 18FxQ20 series, and this one is part 14, Pulse Width Modulation, or PWM. So this is, as I said in the previous video, PMW 6 ways, but in actual fact I found 7 ways of doing it this morning. So it's 7 ways to dim LEDs, but the LEDs are representative of a motor, a switch, lots of different things need these types of signals, a PWM signal. So this is what a PWM signal looks like. It's a voltage, and we chop it up into little signals, and the more we send to it, the brighter in our case, the LED will be, because we're sending it more power. So this is essentially a succession of pulses. You reduce the average power by chopping it up into discrete parts. The average voltage fed to the load, in my case an LED, is controlled by turning on and off at a fast rate. The longer the signal that it is on compared to the off periods, the higher the power supplied to the load. So this way, you can actually have an LED go brighter and dimmer. And how we're going to see it is via an oscilloscope. Not the greatest signal, but I'll come back to that in a minute. So what we're going to do is look through many of the different options, and there's different options on the screen here, and we'll go into each one. This is one option up here: define a constant, define two constants, set up a load of registers. Different ways. It'll all generate signals, which is really good. So what we're going to do though, however, is I'm going to just go over this little I've got a little oscilloscope set up. It's by Gabtronics. It's an XMega XBD Lab, great little thing. And as you can see, I've got the software loaded as well, and I've got it coming through my serial port. It's actually coming through the USB port. And I can then sample that, and we're going to look at that today. So let's have a look at what we're going to do, the 7 ways. The simplest way, number 1, is just turn the port on and off, and you can do that on any port. The next way we've got is we can just send a pulse out for a short period of time on any port, any valid port. Then we have a method called PWMOut, and it sends out a number of pulses on any port. And what is important to those is that you don't need any PPS for those. It's just on any port. But they have different constraints and different use cases. But it's worthy of note to see how they work. Then you've got CCP PMW. And there is a method within GCBASIC that's called fixed frequency, fixed duty. And you need to set up the PPS. And the program does all the heavy lifting for you. It's just great. It just works. Very little, low impact, 2 constants, job done. Then the next way, if you want to have that type of functionality, but you want to be able to vary the frequency and variable the duty, then the 5th way is we have a lot more library or assembler that's doing the heavy lifting for you. And you need to know what that command is. And that's different from the 4th one because that is fixed frequency and fixed duty, but you need PPS on both of those. 6th way, PMW 16-bit way. Wide range of capabilities, fantastic, 16-bit pulse width modulation. Yep, you're going to need the PPS, but you're going to use a different module. It's called the PWM module, and there are lots of parameters or registers to be set up. And the 7th way, which we won't look at today, we'll look at that in interrupts, is you could use the same using a timer and just turn the LED on and off. We'll do that in another session about interrupts. So essentially, we have got 6 ways we're going to look at, but there is a 7th way, which is using an interrupt. So we're going to walk the examples and view the scope each time. Let me go into the first option. Okay, so I'm going to do the header in the program, and then I'm going to dive into the details. Okay, so let me just zoom in for you, shut down the menus on the right. So here we have my chip set up, option explicit. Now I am going to turn off the PPS explicitly because you might be jumping between using non-PPS and PPS. And if you don't set it to 0, it won't forget it. You can power cycle it, but you need to set it to 0. So I'm going to do that anyway, and we're not going to come back to this header for a couple of times now. I've got some LEDs set up on port C, and I've got all the constants set up to make that all work. And essentially, here's my program. I've got a do loop. I'll just indent that for us. And I'm saying flash LED 7, not flash it, invert it, whatever it was, invert it. So that's a not statement. So that could be better viewed as a not statement, just so that you can see it, not LED, not something. It will then toggle it back and forth, and then wait 13 microseconds. So look at the scope. It's just downloading the program. It will flash it. There we go. Turned it off, and we are back to where we were. Look at that. I'm looking on the big scope. That says 38 megahertz. And look, the way that is a PMW signal, and that's at 50% duty. Well, how do I know that? I can see it on the oscilloscopes. But the problem is, of course, if you had a bigger program, it would only send that out during the period that you were doing this. You might have a 4 next loop saying do this 20 times, but you could use, and you can generate a PMW signal using a wait, just toggle it on and off and a wait. But that's not what we're here for. So I'm just going to load in demo 242, and I'm going to look at that. And this one, I'm not going to look at the top because it's all the same. I'm going to bring that down to get it out of the way. I'm going to pulse out. I'm going to pulse out LED 7 for 13 milliseconds and then have it off for 13 milliseconds. This is almost the same as the previous one, but you've got some heavy lifting going on in assembler. So I'm just saying pulse out LED D7 for 13 milliseconds. So I know it's going to be 13 milliseconds, and this one is quite clever because you can really play with the pulse out signal. Look at the scope. It's just downloading the program. We'll see it go flat, and then it will come back up the signal. Hey, trust me, we've reprogrammed it. It's doing a pulse out, and it's sending out a pulse every 13 microseconds, and it's waiting 13 microseconds. So if you wanted to change the duty, if you wanted to play with this, you could go 7:20:19, reprogram it, and we'll see the duty play. It will just play with it a little bit. But you could do this quite easily on any microcontroller. We change the duty. I'll put my demo back because I want to be consistent. Let me reprogram that, and we'll just dump those. We're back now to no programs. Control B. This one needs a bit of explanation. Well, this one called PWMOut on a channel called 1 really shouldn't have that there, to be quite frank. We should have 127, which is 50%. What it's going to do, it's going to send out 100 pulses, and then it's going to wait. And how do we know what this channel 1 is? We have a constant called PWM_out1, and this is a very historic piece of code. And what you need to do is you need to set PMW_out1 to the LED that you're using. You can optionally set this, which I've done, set it to an out. It's not really required, but it's good practice. And we can then program it. And this will send out 100 pulses. There is an issue with this, but it will send out 100 pulses. So have a look on let's have a look on the screen. Why are we only seeing the edge of it? Well, we come out to the software. Let me just bring it up so we can see it. what's actually happening here is, look, is that it is only operating at, I think it's 4 megahertz. That's the fastest this will do it. So this is quite useful. It generates a nice signal for pulses, but the frequency is not that controllable. It's actually very slow because there's a lot of assembler involved. Let me put that back to as it was, and I'll give us more scope. But it generates a square signal. This is what we're here for. Let's look at number 4, fixed mode. Fixed mode requires some PPS. You need to set up the PPS, and you use the PPS tool, and you select CCP1, CCP2, whatever you want to use. And this one, we're using fixed mode, and fixed mode only uses CCP1, and it goes right the way back to the early days of GCBASIC. But it's a very useful way because it doesn't take up much code. If you want to generate a static signal, you set up 2 constants, PWM underscore frequency, FREQ, and the duty one. Set it to 38 and 50, and then you give it a signal called PWM on, and that is it, job done. And there's very little impact in the program because most of this is all handled in scripts at the back end, and it just works. We're back to 38 kilohertz again, look. And if we want to change this to, we want to change the duty, we change the duty here, and we can change the frequency, and we can play with it as much as you like. But it's a static. You can change it. You just have to dig into the code a bit. You can actually change the duty cycles and the frequencies, but you'll have to learn the registers. This needs no register knowledge. The whole point of this is there's no register knowledge. So I'm putting that back to 50% because this is pristine code. And we'll see it flash, drop down, and then go back to the signal we're looking for. So that's just PWM on. I mean, that was simple. Let me trust you, you don't even need these 2 constants. They are automatically defined. So if you want 3850, you just say PWM on once you set your PPS. On this PPS chip, you have to set CCP1 to make it work. Let's move on. This was number 4. Get rid of it. Number 5. Get rid of that. Here we go. PPS is set again. And I've set them all to 1 because all 4 LEDs are coming on. That's the way it works. And down in the program, you say the following. Hardware H PWM 138/127. Well, obviously 1 is the first channel and 38 is the frequency, and then 127 is a function of 255, so therefore that's 50%. That's just the way it works. And if you wanted to change it to a different channel, you change that to 2. If you wanted to change it to another frequency, you change it here. You change it here. So here, you can then have a program that's automatically changing the frequency. Hey, that's clever. You could have a program that's automatically reading in the duty cycle. Ooh, we could do that, could we? Let's look at this. We'll just program it. And we'll see what happens on the scope. And the difference here is that you can have 4 channels. You could use all 4 channels. You can use any frequency that's valid and any duty that's valid. And it's worked. It's done 38 kilohertz. And why haven't I put a demo in there for you? And we'll come back to that shortly. 40. I thought I'd put an ADC in there, but clearly I have mislaid it. Why don't we do that, look? Well, I'm been a bit dim here, look. The code was already there, look. So what we're going to do, I'm just going to uncomment this code here. And basically it defines a variable called ADVal. I read the potentiometer into here, wait 10 milliseconds, and then reset the duty to ADC val. And as ADC val is coming back as 0 to 255, it will go between 0 and 100% duty. Let's have a look. So here I'm going to read in the ADC, set the duty cycle, and then we're going to play with it. Look, watch. Oh, look, it's changing as I rotate the pot. Nothing to full on. Look at that. Isn't that clever? Look. The previous one is using CCP, but it's fixed mode. This just gives you greater flexibility, and you can use any of the channels. Down here, there's an optimization file. So it uses quite a lot of assembler. If you're not using these CCPs, you just set them to false. If you're not using these timers down here, you just set them to false. Otherwise, leave them as true. That way, then you can actually reduce the amount of the program that's in the background. You don't need this. You don't need to optimize it unless you've got a size problem. But essentially what we've got, if we set it up in PPS, this is the command, H pulse width modulation, the CCP channel number, the frequency, and then the duty cycle as a function of 255. Then we're going on to the last one, 6. Totally wrong name, doesn't really matter. This sets registers, but let's go to the PPS. PPS has been changed. It's on PMW. No, it's not CCP. So this is important. You get these right. There's 4 channels. I've written a white paper on this. There's 4 channels that they are in. They're numbered 11 and 12, 21 and 22. And that means that they're joined together in terms of frequency, but you can have different duty cycles within a particular within a double. So that's same frequency. They could be different duty cycles, same frequency, different duty cycles. And you've got a lot more control. But how do you get? I mean, look, I've had to sit down, have I? And forget all that. That's not important. But look at all these registers. I've set registered. I've had to set the external reset. I've selected my clock. I've selected my duty cycle. I've preloaded it. I've set up my next set of channels. Oh my, this is really complicated stuff. And all I'm doing in here is generating a 38 kilohertz cycle. How do you do that? I'll show you how you do it. You load in an application called MCC Standalone. Go to the Microsoft website and download it. I've just started it. I will zoom in on that for you so you can see it. My MP Lab Code Configurator is a standalone tool. New standalone configuration. Just take the default project path, browse to it, and then you see this line here, MCC underscore generated file. Open the right hand mouse button, open a new window. Just open the folder. We'll come back to that in a bit. Okay. Select that folder. Oh, I said take the default, didn't I? Let's do it again. New standalone configuration. I've opened that in here, browse, open that folder, and then just select the default folder. Okay. Next. Now what it's doing with the installation, it's finding all the drivers. Why it finds the drivers before it knows about the chips is beyond me, but it's just weird. Now we don't own this tool. This is a Microchip tool, but it's pretty cool. Watch Q20. Down the bottom, there's my chip. You can't see that, so I'll just move things about so you can see it. Q20. There's my chip there. Boom. Okay, good. I'll move my screen down so you can see it. So sorry. Okay, it's just opened up this very confusing menu. Select one of the 3. It could be melody on the left. It could be classic, depending which chip it is. Select the melody because that's my only option, and then select finish. Now, all that does is you've selected a chip. You've not really done anything yet. First thing you do is set the frequency, load the PWM module in, and we'll just play with it and we'll see what happens. We won't be playing, we'll do it very structured. Okay. So it loads in this little tool, and the first thing we're going to do, I've already said it, is set that frequency, and we're running at 64 hertz, so kilohertz. So let's just clock control, click on that on the left hand side. It will open up a dialog box on the right hand side, which I shall shuffle along so you can see it. And it says here that my clock is currently set to 1, but that ain't right. Internal clock, select 64. It does some processing. It says system clock is 16. That's still not right. Just select the clock divider. Now we've set up our clock. We need to set the clock before we do PMW. That's the way it works in MPLab. Next step, drivers. Cursor down until you see pulse width modulation, and add. Press the plus sign. It will load it in for you. Brilliant. Look at that. It moves it to the top window, and that's where we're going to edit it. It opens up in the right hand side a little dialog, and all you're going to do is leave everything as it is, and let's have a look what we're going to set. Leave the top, that's fine. And we're going to come into here, and actual frequency in kilohertz is 38. Oh, I'll do it in this window here, even better, look, 38. The range in here is 0.97 kilohertz to 64,000 kilohertz. Pretty impressive stuff. And the output is going to be 50, which is great. Now, I already said that in each module here, you can have 2 of these things. So just because I want to prove something to you, just put 100% in the bottom one. You might not use it, for instance. You might turn it off. Set the clock, set the PWM. Then find the generate button, press it, and it's now generated a whole load of code. Remember I opened up a folder? Look, here it is. It's generated some files, and we're going to steal them. System, source, pins, open it up in GC code, and if you look in here, here's the PPS. Oh, we forgot to do something. Back to MCC. We didn't set the pins at the bottom, look, in the pin view. We should do that, really, otherwise this thing won't work. Look, we want to know where we want our PWMout to come out. I want it on this one here, C7. That's the one I want it to come out with. Regenerate, and it automatically regenerates the code. And we've got that over in GC code. Let's have a look what it's done. Oh, look, it's added in a PPS line for us here. And it says in here, look, PPS. So I'm looking in pins.c. And all I'm going to do is I can take that and I can paste that into my code. So C7 equals 7. Look, that happens to be a pure coincidence, by the way. Let's have a look what we've got in our PPS over here. Look. Oh, look, C7 equals 7. It's the same thing. That's cool. We've stolen some code. Back to the folder, pulse width modulation, source. Open up this C source. Then you're going to find the init folder, the initialize. You can take a copy of that, top to bottom. Just go through the whole thing from the first brace to the last brace. Sorry, copy. Go back into our source program. Let me reassure you, I've already done all this, obviously, yeah. I can come into here and I can delete all this. And then I'm going to paste my new code in there. because we should do that. I'm not going to go into the details of what's going on here. We're just going to use it. So there are some things we can just delete because we don't need to explain them yet. Delete the interrupt handlers because we're not going to use them for the moment. Delete anything with bits in it, okay? Because they're all set to 0, redundant setting. And then you come up to a register that's got a value in it. Don't delete it. The rest of it, these are the important registers, okay? Now that's it, because it configures it automatically using registers and it starts it up. Press function key F5, it will compile the code. That's because it just works. If we look in our oscilloscope, we're back to 38 megahertz. Amazing. 38 kilohertz, I can see it on the other screen. And if you wanted to change, this is a 16-bit signal. There's no doubt this is a 16-bit signal. And what I've got in here, look, is how you would then make this variable. Well, let's just have a look at this. My duty is set to a word because it needs to be a big number, and that word is aliased to the 2 registers that control the duty in PWM1 slice 1, high and low. You can see it's just an alias. So if we set my duty to a big number, a number, it will automatically get written to those registers via the alias command. Define a variable that's got a word range, read in the ADC, put it into my ADC value. This is long-winded, by the way, because I could have just put the read value, the read AD10 in here, and then I scale that number to a maximum of 728. Oh, where do I get that from? Well, in reality, we set one of those duty cycles to 100%, and that 100% is that value of exactly 728 in hexadecimal. Now, so that means we're going to read in the ADC, set the registers, and then you just have to load the period and duty cycle registers on the next event. And this is this is 1 bit inside of the hundreds of bits that are in there. It's 1 bit called PWM1con underscore LD. But because the way that Microchip name their registers and bits, it's the other way around. You just have to find it. And I found it very easily using PIC-info. Here it was here. It was in PIC-info and I can see it's on the screen. You can't quite make that out. I'll just zoom in on that. It was in here. I had to go into here and go, oh, what's that thing called? Look. And I looked for PWM 1con and thought, there's the register there. Look, okay. And it used to be called LD, but they've renamed it on this particular chip. What this does, this command here, it actually loads the duty register. Function key F5. Function key F5 programs it. We've seen that many times. And I am changing the duty. Now, I've obviously, for the rocket scientists out there, yeah, the range is no longer 16-bit because the range of the ADC read is only 10 bits. So the ADC on this particular chip really should be a 16-bit ADC, but it's not. So, but you have the range. You can do it in your own way, okay? But there's a limitation, not in the GCBASIC, but it's just in the way that we'll read in the ADC. And you can see that is getting smaller and larger. On my very expensive oscilloscope, these are beautiful square waves. Look at that. That's fantastic. Full on. It's full on. Okay. We have looked at pulse width modulation 6 ways, and there's a 7th way, which we'll talk about another day. This is the longest video I've done. It is quite complicated in terms of covering the scopes of pulse width modulation. Next time we're using an external interrupt to do the same, but we'll also use an external interrupt to sequence the LEDs. Then after that, we're home and dry. We're into the back end of this set of videos. So enjoy this mega video, like it, thumbs up, etc.